Example 4 is a little bit longer of a problem, and it's still a separable differential equation, but the way the function starts out right here, our y prime equals x squared plus 3y squared over 2xy, it currently isn't in a separable form, but this type of an equation we can make separable by using a substitution of y equals v times x. So let's see how this one works here. I'm just going to rewrite the original equation. So y prime is equal to the x squared plus 3y squared, all divided by 2xy. My substitution is y equals vx. So not only do we need to substitute in this expression vx in for the two y's on the right-hand side, we also need to substitute in what y prime is equal to. So I first need to take the derivative of this substitution equation. So when we do that, I get y prime is equal to, but this is a product, and both v and x are actually can be thought of as functions. V is a function of x and y, and then x by itself is also just a function. So I need to throw the product rule at it, which means the derivative of the first would be v prime times the second, which is x, plus v times the derivative of the second function, but the derivative of x is just 1, so I can kind of leave off that multiplication of 1. So there's my two substitutions. So on the left-hand side, v prime x plus v, that's what y prime is equal to x squared plus 3 times y squared. Let's see, if I square y, that's actually going to be v squared, x squared, 2, divided by 2 times x, again multiplied by y, or vx. So I'll multiply by another x to make it x squared, n times v. So x squared v. Also, as soon as we did that, you can see that we've got two x squared terms in the numerator and 1 in the denominator, which means we can factor out the x squared and cancel them. So on the left, I still have v prime x, let me back up, v prime times x plus v. We'll factor out the x squared. That will leave 1 plus 3v squared, all divided by 2 x squared v. And let's cancel out the x squareds. So now I have v prime x plus v equals 1 plus 3v squared over 2v. So from here, let's subtract this v term out, and I'll get v prime x on the left, 1 plus 3v squared divided by 2v minus v. And I actually want to subtract and combine the two terms on the right-hand side. So I'm going to multiply the top equation by 2v. I need to get a common denominator. So I multiply by the bottom by 2v and the top by 2v, so that'll make it a v squared. And now I can combine these two terms on the right-hand side, and I'll have a common denominator of 2v. It'll be 1. 3v squared minus 2v squared leaves me with 1v squared, or just v squared. And from here, we can finally make this separable, in that if I write it as dv dx times x equals 1 plus v squared over 2v, I can cross-multiply up my v, so 2v up to the left, divide 1 plus v squared down to the right, and then I can do the same thing with my x's. I can get the x down and the dx up. So when I do that, let's see what we end up with. I'm going to come up to here, see if I can fit it in. So on the left, I'll have a 2v over 1 plus v squared, and that'll have a dv. I'm going to divide by x, so on the right I'll have 1 over x, multiply up by dx, and from here I can integrate these two expressions. So on the left, using a little guess and check, I can see that, well, this possibly could come from the natural log of 1 plus v squared. And to check it, I know the derivative of the natural log of anything is 1 over that anything, so 1 over 1 plus v squared, which I have right here. And then the derivative of the inside is just 2v, which I have right up here. So we do have the antiderivative of the left-hand side. Same thing on the right-hand side. I know that that's going to come from the natural log of x, and technically the absolute value of x, but I can see that we're using x as a positive 1. So I'm going to leave off the absolute value for now. I don't think we'll need it, so let's just do the natural log of x. But I will have a plus c. So from here, we just need to solve for v and eventually back substitute what v is equal to, which would be y divided by x, and try to get down to a solution for y. So from here, I'm going to take the exponential of each side. That leaves me with 1 plus v squared on the left. On the right, I can rewrite that as e to the natural log of x times e to the c. So on the right, the first term really is just x, and the second term, e to a constant, is still a constant. So I'm going to put that as a c1 out front of the x, and I get 1 plus v squared. So a couple more steps and we have solved for v. What we would need to do is subtract a 1, so c1x minus 1. This might be a good time to actually do our substitution of what v is. And then if I come up here, I can see that v is really going to equal y divided by x. And when I substitute that in, it's really v squared. So it'll be y squared over x squared. So need a new page here. So I get y squared over x squared is equal to c1x minus 1. Cross multiply by x squared. That's going to leave me with y squared equals c1x cubed minus x squared. And at this point, let's solve for our constant, our c1, which I can see my initial condition is y of 1 is 1. So if I use y of 1 is equal to 1, what that will imply is, let's see, 1 squared is 1 equals c sub 1. X is 1, so that's just c1 times 1 minus 1, and I can see that c1 has to equal 2. So I have now, if I substitute that back in for c1, I have y squared equals 2 x cubed minus x squared. And my last step is to take the square root of each side. Again, we would get a plus or minus, but I can see that y is positive, so it's going to be the positive solution. So I finally have y is equal to the square root of 2x cubed minus x squared, and that should be the solution to our differential equation. And if we want to figure out which part of the integral curve I have graphed, if we go back up here, it looks like it should be the integral curve that goes through where? Let's see. When y is 1, x is 1, so that's x is 1 here, y is 1 right about there. So it looks like it should be this curve right here is what we just found for our solution. And if we take a look at Sage Math, what this looks like, let me jump over to Sage Math here, which is this one. This first command up here on top, let me change it a little bit, get that out of there, and get this out of here. So here's what the slope field looks like that was on the handout. So as far as the code goes, I define my two variables, x and y. P1 is I'm making a graphic object that's plot slope field, and here was our y prime, x squared plus 3y squared, all divided by 2xy. I plotted it from -5 to 5 on both the x's and y's, and then the next line is commented out with this pound sign. So I just want to show what P1 is, and if I evaluate it, yep, there's what my slope field looks like. Now I can create another graphic, let's call it P2. This is our solution curve. It's the square root of 2x cubed minus x squared. And let's say I plot it from, first I want to go from, well, let's go from 1 to 2.5, because we know y of 1 is 1. So when x is 1, y is 1. So we should be able to graph x's from 1 to 2.5. Let's see what that looks like. Not there. Oops, and I need to do plus P2 to show both of them. Try it again. There it is. So it does look like it starts at 1, 1, and then goes up to the right, like our integral curve that we kind of sketched in. But I want to maybe make it go down to when y is 0. So I might guess at it that if I put in a 0 and plot from 0 to 2.5, what do I get? Ooh, I get bad errors. Something's wrong. It can't plot some of the points that I put in. So question is, why? The reason is I can only start at 0.5 to graph our function. X is 0.5. And now I get a nice curve that starts when y is 1 and continues up. So what's happening between 0 and 1? Well, if we graph what's underneath the square root, just this expression right here, if we just graph under the square root, that's a cubic, and what it looks like is that function right there. And you can see between 0 and 1, or 0 and a half, it's negative, and obviously you can't take the square root of a negative. So if we wanted to try to find that interval of definition, which wasn't asked on this problem, but if we did want to find the interval of definition on that, we can do that kind of like what we did in class. Let me find where we were at. Here we are. If I take, let's see, let's turn it this way. If I take what's inside the 2x cubed minus x squared, that needs to be greater than or equal to 0. I can add the x squared to the right-hand side. I know x squared is always positive as long as it's not 0. I don't want x to be 0, but we know we're not going to be starting at x is equal to 0. So I can divide each side by x squared. That will give me 2x greater than or equal to 1. And finally divide by 2, x is greater than or equal to a half. So that's why we needed to start when x is greater than or equal to half, and that starts us out right at the beginning of that curve when x is 0 there. So hopefully that helped looking at a couple of these problems, and we'll do some more tomorrow.